Hello, this is Concrete Path. Today's lecture is about the problems associated with your bending stresses. So let's take the problem one. So lecture one, that problem one that says the section of the beam is a rectangular section of width 30 mm and a depth equals 100 mm. Say this is the ZZ axis of the section and this is the YY axis of the section. Now the beam is such that you have a loading of UDL acting for one half of the span, that is 2 meter, and a loading intensity of 3 kilonewton per meter. And the loading is such that loading is parallel to Y line. The first case of the problem is that the loading is parallel to Y line. That means the plane of loading or plane of couple, that is Y plane, we can say. That's parallel to Y plane. So if we say let's take that. Now let's calculate we need the bending stress maximum. So we need maximum bending stresses. We need maximum bending stress. For that you need maximum bending moment in the beam. So from the shear force diagram and bending moment diagram, you can have a maximum bending moment somewhere here after 2 meter. So let's calculate that value. So here the reaction we can get 3 to the 6. So you can have centroid here. So we can have 3 to the 6 into length of 3 into length of 1 and divided by 4. So we can get a reaction of 1.5, and we can write the bending moment value here would be 1.5 into 3 minus 3 into yeah. We can get the bending moment value. We can't get directly. We don't know where the bending moment would be, maximum. So for that we have shear force equals to 0. So we at the location of shear force equals to 0. Let's say this is the shear force location where the shear force is 0. We write shear force at x equals to 0. We write 1.5 kilonewton reaction minus W intensity into x. So a length of, actually we have to write this one at x minus 2 meter. So we can write 1.5 minus 3x plus 6 equals to 0. That means your x value of 1.5 meter. (7.5 by 3). That value we can get 2.5 meter. That means at 2.5 meter, so this is 2.5. So here the bending moment would be maximum. So we can write the value of bending moment would be here 2.5. So we can write shear force, that reaction into 2.5, 1.5 into 2.5 minus that loading intensity of 3 into, for a length of 0.5 squared by 2. Let's say you got a bending moment value of 3.375 kilonewton meter. So you got the maximum bending moment. Now you want to say, so plane of loading or plane of couple is parallel to Y plane. So we have plane of loading parallel to Y plane. That means plane of loading is this one, and bending stress, and let's say this is the moment Z direction. So this is perpendicular to it. We can say neutral axis is also in this one. Neutral axis is parallel to Z direction. So we can calculate the section modulus from this one. So we write bending stresses, or we can write sigma max equals to M max, moment max, into Y max by I neutral axis. But I neutral axis should be about the axis ZZ, IZZ. So this is our ZZ axis. So we write IZZ. So if you calculate that, if you use the value 3.375 kilonewton meter, and value of Y max equals to that 100 by 2, 100 mm by 2, and divided by neutral axis, that second moment of area about neutral axis. So we write the 30 into 100 cube by 12, that mm power 4. let's say you got a value of that is sigma max equals to, that's in x direction, so you got a maximum value of bending stress 67.5 megapascal. Now, so for this case, when loading was parallel to, when the loading was parallel to YY line, so your beam was deflecting, so the bending was in this way. So plane of loading was YY plane. So this was plane of bending. So now if you question, the question is designed, say it says that loading is perpendicular to Y line. Now if the loading intensity UDL is perpendicular to Y line, that means if you reverse the section, let's say this was your simply support beam. Now you reverse the section. Till earlier we had a section which was in this fashion. So we had a section which was having a width of 30 and a depth of 100. So this was along Z, this was along Y. Now if the loading is perpendicular to Y, so this is Y and loading is perpendicular to, now earlier it was parallel, so loading was parallel to Y line. Loading was parallel to Y line. Now the loading should be perpendicular to Y line. So let's make that in this way. Let's reverse the beam. Say this is the beam. Let's take this as a beam. Now the loading is reversed. Now the loading has changed its direction. Now let's say this is our, till now it was your B, now it has changed to D, and this is our B. So loading is acting. So load is acting in this way. This is loading, but it is perpendicular to B. So your B was, earlier the y-axis was this one, now y-axis has changed because we have reversed the dimension. So this is your y-axis and this is z-axis. So neutral axis would be around this one. So if you take this section, you have depth D and here have width B, then you take that neutral axis. So this is neutral axis, this is around IYY. We can say that this is the line of YY. This is YY line. Then we can write what is the value of IYY, that's equals to DB cubed by 12. And Y max, we can say Z max, we can't say Y max. Let's write Z max. Value of Z max equals to, so now the neutral axis is this one. So the value of Z max equals to Z max. Z max equals to Z by 2. That B by 2. So now the bending stress maximum, sigma max bending stress maximum in the x direction because of the loading that's perpendicular to y direction. Then we have that moment max, then IYY and my by I, mz max by IY. So we write the value of bending moment is not a function of section. So moment is not a function of section. It's not a function of section. So moment value is remain constant, 3.375 kilonewton meter. Only your parameters of section change, that the directions of those neutral axis changes. So you write Z max equals to B by 2. Value of B was 30 divided by 2 mm. Similarly, you write D. So your depth, value of depth is 100 into 30 cubed by 12 mm power 4. So you got a stress value. Let's calculate those stresses, and we say there are two different stresses. Let's take one more problem. Let's take one more problem. So you had a cantilever beam, but the cross sectional is circular. So you had a circular cross sectional beam. You're applying a load of P. So we know that maximum bending moment would be at the end support or at the cantilever side. That equals to PL. So if you want to say what's the value of maximum bending stress, that equals to maximum bending moment into your value of that Y max. So if you take any section, because your that beam is prismatic, that means cross section remains constant throughout the length. If you take any section and you have a neutral axis perpendicular to the load direction, so you have neutral axis that perpendicular to plane of bending. So this is your Y max. y max equals to d by 2. And we know that I neutral axis equals to pi d 4 by 64. So you write PL by and my by I. Then you got a value of that you calculate PLD, whatever you got value. So you calculate that. So you got the maximum stress. So this was the case that your cross section was constant throughout the length. Now if you want to take that any uniformly varying cross section, let's say you had same beam but the section is changing, diameter of the beam changes. Let's say the diameter is here is d1 and the diameter at the end is d2. So you want to say what's the maximum bending stress? What's the maximum bending stress? And so maximum bending stress, it is a function of moment, it's a function of y, and it is a function of I. So your all the values of the all three values vary with the length x. So we say that let's say that at any x we say that bending stress is maximum at x. Let's say maximum bending stress is at x from free end, because these are all variable. All three are variable. So we don't know where the maximum bending stress would be. So let's say that at a distance x we have maximum bending stress. So for that you need the diameter of that section x. Let's say the diameter at section x equals to dx. Let's say this is dx and this is your neutral axis and this is diameter dx, and y max, we know y max would be dx by 2, and we know that that I neutral axis above moment of inertia about neutral axis would be equals to pi dx power 4 by 64. But what's the value of dx? You can say by the linear variation we can say dx equals to d1 plus the change. This difference is the change in the length L, total length of L, but I need for the change for a length of x. So let's call it as d1 plus kx. Dx equals to d1 plus kx. So we got all those values. If you want to say what's the value of bending moment at this x, so you had a beam, you're applying a concentrated moment, that concentrated load at the end. You have a load of P here. So here the internal force, that shear force, would be equals to P, and the bending moment developed would be P into x. P into x. You write that P into x. So we got all those values. We can write that sigma at x equals to P into x into y max. Y max was dx by 2, and ix was equals to pi d. Ix was equals to I neutral axis about that point, but at that point s. I neutral axis about that point x. At that point x. Pi to the power pi by 4, pi by 64 into d to the power x, dx power 4. Dx power 4. Now you substitute the values, you know that dx value. So we can say px by 32, or we can say 32p by px by pi, and we have left with dx cube. The value of dx was equals to d1 plus k times x whole cube. Now this is the value of bending stress at any x from free end. So we want it to be maximum. We want it to be maximum. So that means if you minimize it, let's minimize it with respect to that x. So we can get value of 0. So let's differentiate it. So we can say let's say that we get a value of that x, or we can say d1 plus kx whole cube into 1 minus x, and you have this one 3 times d1 plus kx whole cube whole square into constant k equals to 0 divided by d1 plus kx whole cube and whole square. So you differentiate it, that equate it to 0. Now we can say we can say now, let's say this one would be 0. Let's take this as 0. So we can say d1 plus kx whole cube minus 3x 3kx and d1 plus kx, that equals to 0. That means d1 plus kx whole square. Yeah, this was square, so we can take this common, so we're left with d1 plus kx minus 3kx equals to 0. That means d1 equals to 2kx. d1 equals to 2kx. So if you substitute the value, if you want to say what is the value of x, so you can get the value of d1 by 2. The value of k was equals to d2 minus d1 by L. So you got the value of x, the location of x where the maximum bending stress would be there. So if you calculate the maximum bending stress now, if you calculate the maximum bending stress, that equals to p into x. This was your p into x, and then the value of dx. So we can say dx by 2. Finally, you got that as 32p by pi, and the cube of that one, d1 plus kx, d1 plus kx. The value of kx was d2 minus d1 by L, d1 plus kx, d1 plus kx. And the value of k into x, the value of x is itself d1 by 2, d2 minus d1. And this was d1 plus kx whole cube. And finally, you got this bending stress maximum. And if you know the values, and you can substitute the values, this is your maximum bending stress. So the result is that the maximum bending stress occurs at x equals to d by 2k, d1 by 2k. Then finally you can substitute the values. So main conclusion is that the length of the location of x from the free end is at a distance of d1 by 2k, where your value of k equals to d2 minus d1 by k, d2 minus d1 by L. So we have a problem of that. We had a problem that we have a square section. We have a square section. We have a square section. Now we have two different configurations of that section. So firstly we place the section such that the neutral axis, it's parallel to one of the sides. So this is your side A. All the sides are square, so we say all sides are equals to A. So neutral axis is parallel to A, side A. And next case is that you have a neutral axis parallel to diagonal, one of the diagonal. Let's say this is a square and the neutral axis is parallel to one of the diagonal. So side of A. So your neutral axis is parallel to diagonal. So you want to say what's the ratio of Z, section modulus ratio of Z. That indicates the section modulus ratio indicates which one is your having more bending strength or more moment of resistance capacity. Yeah. So if you say what's the value of Z, if you calculate for the first one, Z1 equals to, we know that I neutral x is 1, I1 by y max 1, y1 max, and Z2 equals to I2 by y2 max. Let's say this is y1 max and this is y2 max. So y1 value equals to a by 2 and y2 equals to that if you have this triangle, this is a and this is 45, this is a by root 2, this is also a by root 2. So you got a value of a by root 2, y max equals to a by root 2, y max 2. So, and also the value of I, we know I for the rectangle we have value of I equals to b d cube by 12. Then you can write a power 4 by 12, a power 4 by 12 into value of a by 2. So you got a value of a cube by 6. And for this one, if you use the parallel axis theorem, that you have a triangle of depth that a by root 2 and a width of this width of root 2a. Is it root 2a? This one is a by root 2. A by root 2 plus a by root 2. That is 2 times a by root 2. That is root 2a. So you got this one rectangle. So you know this, that moment of inertia about the centroidal axis. Then you do parallel axis theorem plus area of that triangle into that distance of whatever distance, that 1/3 of a by root 2, and that equals to some d. So you do d square and you get a value of I. Then similarly, if you have two triangles, finally you get a moment of inertia about this axis, that is neutral axis. You got a value of neutral axis equals to finally same as that of a square, that is equals to a to the power 4 by 12. That is the same value as you got for the rectangle, a to the power 4 by 12. So you write the value as a to the power 4 by 12, and you have a y max equals to a by root 2. From this one, y max equals to a by root 2. And you substitute, you write that z1 by z2 equals to, when you substitute the values, you can write a cube by 6 into a power 4 into a 12 root 2. So you got a value of z1 by z2 equals to root 2, 1.414. That means your z for the square is greater than z for that rhombus, or we can say diamond. So your section, you can say rectangular section or square section, is better than this one. So bending strength of rectangular section is more than that of a. This concludes that bending strength of rectangle is more. Yeah. Now we have one more problem. That's saying that we have a log of wood. So we got one wood. We got a log of wood. Now you do one thing. You make a circle. You make a rectangle of that. So we say this was your wooden log. Wooden log was given to you. You cut it from the sides such that you make a beam that is strongest. Make a strongest beam. Make for us a strongest beam. That means a beam having bending strength, more bending strength. That means your bending strength is more. That means your section modulus should be more. Your bending that if your section is strong, that means it is stronger in bending. That means your section modulus should be more. Z should be more. Let's cut the section to make a. It's mentioned that you have to make a rectangular beam. Make for us a beam that's stronger. Rectangular beam. So whatever. Rectangular beam. Let's say we are making a rectangular beam out of that. So this is we have to make. Let's say that the diameter of the beam, diameter of the circle, the wooden log, diameter of the wooden log was equals to diameter d. And let's say you have cut the beam. So this part you have removed. This part you are removing from the wooden log of circular diameter. This part you are removing. Finally, you are receiving a beam of width, the depth d and width b. So the width b and depth d, and this should be, z should be maximum. Z you have to maximize such that your bending strength is maximum. So let's say we want to maximize Z maximize. So we can maximize it with respect to b, or we can maximize it with respect to depth. It's up to you. Let's convert one of those parameters in terms of other. Let's calculate that. We know that from the triangle we can say d square plus b square equals to d square. Can we say that? Now if we substitute the value of, say, if you take the value of d in terms of, if you take the value of d square in terms of d square minus b square, now we got this one. Now we know one thing, that the value of section modulus for the rectangular beam equals to, let's say this is our reference neutral axis. Let's say this is neutral axis. We can say what's the value of z, that equals to b d cubed by 12, and we have that y max equals to d by 2. So we got a value of bd square by 6 z. So we want this z value to be maximum. So we substitute the value of d square equals to d square minus b square. So we can write b times d square minus b square by 6 to be maximized. We want to maximize this one. So let's say dz by de with respect to b. Now we have only one variable, that's b. So we say dz by db equals to 0. That means differentiation of that function, that is bd square minus b cubed by 6, that equals to 0. So if you use the values, so we get a value of that d square minus 3b square equals to 0. That means your width, that width of the beam should be equals to d by root 3. And similarly, if you substitute the value of d square equals to d square minus d by root 3 whole square. So you got a value of root 2 by 3 of d. And finally, you got a value of z max, that equals to bd square by 6. bd square by 6. So finally, you got a value of z max. So z max equals to d cubed by 9 root 3. d cubed by 9 root 3. So if it was a square, section such that the diameter here is d, so we got a value of d. Let's say the diameter of the square. Let's say the diameter of the square was d. So we got a value. We could have a value of d cubed by 6. We could have a value of d cubed by 6. And in this case, when we cut from the circular wooden log a beam of BD, so we got a value of Z max equals to, in terms of diameter D, we got a value of D cubed by 9 root 3. So let's write some interesting facts. Let's write the interesting facts. So let's say you have a beam of that diamond section. So this is neutral axis. So let's say the section modulus is Z of this beam of section, that rectangle, that diamond section. Now you are cutting that ends of the section. If you are cutting the ends of the section to a distance of that x equals to, this is x equals to, let's say the side of this beam is equals to a, and you cut a section equals to x equals to a by 9. So if you cut x equals to a by 9 along this side, so from the both sides of the beam, from the top and bottom, then your bending strength increases by 5.35% about that neutral axis. 5.35%. So because your z is a function of I by y, even though y value decreases, even though your value of I decreases, but based on the fact that y also decreases, so finally your z net value of z increases by 5.35%. Similarly, we have one more that is circular. So we have circular section. If you cut that from the top and bottom to have, let's say total diameter is d. If you cut 0.11d, 0.11d, if you cut this part, and your bending strength would increase. Bending strength increases. Bending strength increases by amount of 0.7% about the neutral axis. Now let's take the problem that we have a non-prismatic beam. So So we have a beam of cross section of square for a length of, let's take that length of, let's say the total length of the beam is 7.5 meter. Now you are applying a moment, you are applying a load in the direction that is, let's say the direction is along the diagonal. So you're applying a load of P equals to 4 kilonewton along the diagonal. So that means if you have a beam in this fashion, you're applying a load of P here. So the neutral axis is this one. So the neutral axis forms this one, neutral axis. So let's call that as a ZZ axis. So let's say this is your ZZ axis, and this one, and you call the direction of P equals to as YY direction, and downwards you call as a direction of X. Call downwards as a direction of X. You want to say what's the value of maximum bending strength? Value of maximum bending stress. What's the maximum bending stress that can be developed? So we have maximum bending strength equals to moment max, but it's a function of three variables. We have moment at any x, y at any x, and I at any x. So because the section is also changing, so your value of y and I also changes. So you can't say directly that moment at the maximum location, that's at the end support, at the end we can have maximum moment. No, sure, that's for sure, but the value of y and I also changes such that it can be the net value of bending stress would be maximum anywhere at a distance of x. So let's say that at a distance of x you have a maximum bending stress. That means on this cube, on this square of side ax, let's say this is the square of side ax, such that this is your neutral axis, and on this one you have to see how much moment is applied from the free body diagram. Say you're applying a load of P here the moment developed would be P, the shear force P, and a moment of P into x. Let's say P into x. Anti-clockwise, clockwise, it is not that critical for this problem. Let's say that you got some bending moment of px. So we got the moment px, and we got the section ax, and we got the section modulus. We can solve that is equals to ax power 4 by 12, and a value of maximum. What's the value of maximum? Place it on this one. What's the value of y max? From the neutral axis, we can say if the side is ax, So we can write ax by root 2, ax by root 2. So we write ax by root 2. So we got the value of zx, and value of mx we also got as bx. So finally, if we want to say the maximum bending strength, we want, if the sigma x, we want to maximize it. So we write that p into x, let's say the value of p was equals to 4 kilonewton. Let's keep the value of p, and let's keep the value, let's use it as in sign of p. So we're at px into value of zx, px into section modulus m by z. Your sigma equals to m by z. So you write zx, and you substitute the values. We can write px by ax cube root 2 into 12. 12 ऊपर जाएगा, yeah, 12 by root 2. So we got this value of bending stress, px 12 by ax power q, ax power 3 root 2. So if you use that, if you are provided with the values that it's varying with the length, it's varying, the square cross section is varying from a section side of 75 mm to a side of 150 mm. So if you say what's the value of that side at any x, we can say side at any x equals to 75 mm plus the change is 150 minus 75 in the length of 7.5 meter. And let's say that you go to a distance of x meter. Let's call it as x meter. This is also x meter. So you got an equation of ax equals to 75 plus 10x, where your value of x is in meters. So you got a value of 75 plus 10x. And if you substitute it here, so you can substitute the value here. So you write p 12p into x by root 2 into ax, 75 plus 10 power x, 10x whole cube. Yeah. So this should be maximized. So we can maximize it with respect to x. So that means we got a value of 75 plus 10x whole cube into 1 minus x into 3 into 75 plus 10x square, and a constant of 10 that equals to 0. So finally you got a value that 75 plus 10x minus 3x into 10 equals to 0. So that means your value of x equals to 75 meter by 10, 20, yeah, 20. So we got a value of x equals to 2 3 7, 3.75 meter. You got a value that if you go to a distance of x equals to 3.75, so at distance of x equals to 3.75, here is the diameter ax, such that the bending stress would be maximum here. So if you want to calculate the maximum bending stress, so let's calculate maximum bending stress. So let's use the value of x equals to 3.75. So let's substitute the value of p also. P was equals to 4 kilonewton. And value of x equals to 3.75 meter. And 75 plus 10 into x. Value of x equals to 3.75 meter. And you calculate the values, and you would get a bending stress value of maximum that equals to 89.39 megapascal. 89.39 megapascal. Let's take one more problem. Now you have I section beam. Now it's continuous. We can say this is continuous. Let's say this is fixed from this side. Now you are applying a load. Now you're applying a load of 10 kilonewton. Let's say let's make the line diagram first. So you're having a point load of 10 kilonewton for the length of 2-meter beam. So the dimensions of the beam, you can have the dimensions of the beam that 20 mm. This one, thickness of web is 20 mm, and thickness of web is 20 mm. Thickness of flange is also 20 mm. Then width of the flange is equals to 200 mm, and thickness of web is such that the total depth equals to 300 mm. So these are the dimensions of the beam. Now the loading is that it's not along the principal axis. So we have two principal axes. We know that we have two principal axes. One is this one, along which product of inertia is 0, and next one would be perpendicular to that. But loading is not passing through the principal axis. But loading is such that it's making an angle of 30 degree with respect to vertical. So it's making an angle of 30 degree with respect to vertical. So this is your load P. So load is acting in this way. So P is acting in this way, P. So it's making an angle of 30 degrees. So if you resolve that, so you had to resolve that to make it acting for the symmetric beam, we can say symmetric bending. For the symmetric bending case, we had to ensure that load is perpendicular to principal axis, because during the derivation of flexural formula, this was our assumption that load should pass through the principal axis. That load should be perpendicular to the principal axis, or we can say load should pass through the principal axis. One of the principal axis it should pass, and other it would be perpendicular. So the load should be passing through the principal axis, and it would be perpendicular to the other axis. Similarly, if the one component is passing through the one of the axis, that is perpendicular to the other axis. So we had to resolve that vector of P. Let's say that. Let's resolve that. So this is your vertical. This is your horizontal. So load is acting in this direction P. So we can say this is theta. So this is your loading intensity in y direction would be P cos theta, P cos 30. And in the horizontal, you could have a horizontal load that in the z direction, you can say it's in the z direction, and this was in the y direction, and this is in the z direction. That is P sin 30. Now we can show that the load, this one would be, this is our PZ, because this is z direction, and this is y direction. So we can say this is our load of Py. So we can solve individually and then superimpose the effects. Now if you say for the derivation we say that loading plane is y plane. We have the loading plane that's called as plane of loading. That was y plane. For the during the derivation we have loading plane that was y. So if you solve for y, then we said that top members are that having compression, and bottom members having tension. So let's take tension as positive and compression as negative. We say that bottom fibers are having tensile stresses, and top fibers having compression. But this is not the case. This is a cantilever beam. This was valid. This was valid when we have derived that flexural formula. We said we applied a moment of that positive bending moment. Because of that, we had sagging curvature. Now this is during the derivation. But if you talk about the cantilever beam, let's say you are applying a load of P here. So here the moment developed would be P into L. That's anti-clockwise. So if on the section you have anti-clockwise moment, that means you have a hogging curvature. So your hogging curvature would be developed. So your beam would deflect in this way, such that If you draw that, you have this one. So your bottom members have compressed. Bottom members got compressed. You can say compressed, and top members have got stretched, so tensile stress. So on the top you have tensile stresses, on the bottom you have compressive stresses for the cantilever beam. This is the difference between that if you have simply support beam subject to moment and that as that of a cantilever beam. Because in the cantilever beam, a hogging curvature would get developed. Let's say the load was upwards. If the load was upwards, then there would have been a that moment developed, that is clockwise moment, positive moment, PL. So then the curvature would have been in this way, compressive and tensile. So you could have the same value, same nature, that this is compressive and this is tensile. But in this case, you can have that stress variation as this is tensile and this is compressive. So the top is positive and negative is downward. So this is neutral axis. So bottom is having compression, and finally top members having tension. So this is you have to remember that, this one, because M is anti-clockwise hog. So finally we got that. That means if you note if you represent that the corners of the beam A, B, C, D, I would say that for the loading, let's say for loading vertical, that is for PY loading, for loading PY, this one, because of that anti-clockwise moment would get developed, and that is say moment Z, that would be a moment Z. That means your top fibers up to the neutral axis would be having tensile stresses. So your variation of the stress would be in this way. So we can say that your variation of stresses would be such that on the top we have tensile stresses, and in the bottom we have compressive stresses. So the members, all the members above neutral axis, ZZ axis, neutral axis. So these would be having a stress of tensile. So we can write A, comma B is having a tensile stress. For the loading PY, your AB is having a stress of tensile, that's positive. And for the BC, for the CD corners, we can say these two. For the CD corners, this one and this one, you have a compressive stress. That is negative. So we have compressive stress for C and D for the loading PY. If you talk about the loading PZ, so let's talk about the loading PZ. Let's make the diagram separately. So loading is acting in this way. So let's make the diagram. So you have this beam. Now the section is such that it's a I section. It's a S section, I can say, because the loading is acting along the H section, So I have to make an SH section. Let's make an H section such that this one. So now the load is acting along this axis. So load is acting in this way. So this is your load in the Z direction. So this is your ZZ axis. That means the neutral axis would be along the YY axis, neutral axis, for this loading. Now you have this loading, and the beam is continuous for a length of 2 meters. So you have this beam now. So you are applying a load of PZ that was equals to P sine 30. So P by 2 load. So because of that you have a hogging bending moment developed at the support, P into L. Yeah, P by 2 L. And finally you can say the top members would be having that tensile stresses, because hogging curvature, that means top is having tension and bottom compression. So finally he can write that if you say what are the four corners, how can you mark those? This is corner 1, corner 2, corner 3, and corner 4. Initially the corners were ABCD. So initially the corners were at, so this was ABCD. Now what had happened? So this was ABCD. Now we have reversed the direction. So we are saying on the top we had B and C, and bottom we had A and D. So BC is at the top. BC is at the top. BC is at the top. So this is B and this is C, and we have A, B, C, D. So we have rotated, actually we have rotated from the initial position, we have rotated the beam by an angle of 90 degrees anti-clockwise. So we got this configuration now. Such that we can say B and C is having tension, B comma C is having tension, and C, A and D is having compressive stresses. So finally we got that we can say that A is having, so A is having in this part A is having tension, and in the second case A is having compressive stresses. A is having tension and A is having compression, but in the case of loading Y and in the case of loading Z, the loading was in the Z direction. And similarly your B is having tension for loading Y, B is having tension for loading Y, and B is having, in this one, for the loading Z, B is also having tension again for the loading Z. Similarly you can say for the C you have initially you have compressive stress for the C. Initially you have compressive stresses for the C. You have compressive stress for the C for the loading of PY, and you have tensile stresses here for the C. You have tensile stresses here, tensiles for the loading of PZ. Similarly for the corner D, you had initially you had a stress of compressive stress for the loading Y. So you had a compressive stress, that is C, for the loading of PY, and similarly you have a stress of compressive for the loading Z. So we can say that out of those four, two are alternate. A and C is having alternate values, and B and D is having same values, either tensile or compressive. So we need to calculate those the stresses at those four corners. The bending stress, when we know that bending stress equals to M Y by I, only we need to say what's the value of Y at the different corners. That's we say Y max at the different corners. So either we have these four corners from the neutral axis, we say Y would be this one for for all those, because beam is uniform, beam is symmetric and uniform. So all those four corners we would be having Y max same. And if you take that S section, for all those four corners you have Y same, or we can say Z is same. So, and you need to calculate Ix, or we can say IZZ, and you need to calculate Iyy, and that's also constant, some value constant, and moment is also constant, M is also constant. That is a function of load, total component of that load along the particular direction into length of 2 meters, and this is also constant. So you need to just see this now, this direction of those, either it's compressive or tensile. So that we have to see. So let's solve the problem now. Let's solve the problem now. So So we need to calculate the components. The components we have P cos theta and P sin theta. Is the value of P given? Yeah. The value of P was equals to 10 kilonewton. P was equals to 10 kilonewton. 10 kilonewton. That means Pz would be equals to 5 kilonewton. And Py would be equals to 10 into root 3 by 2. That equals to 8 point something. 8 point. Let's keep it as it is. And if you want to say, now you are applying a moment, now the moment would be applied. Let's talk about the direction of py direction. Let's say this is the py was equals to 5 root 3 and length of 2 meters. So maximum moment would be max would be equals to 10 root 3, that is 17.32 kilonewton meter. Now based on the moment, see, we know that moment is negative anti-clockwise. Based on this we have drawn those corners. Based on this fact that we have drawn the corners. Now there is no need of this sign. There is no need of the sign that moment is negative or positive. See, we have already drawn the negative and positive based on the fact that moment is anti-clockwise. Based on the fact that moment is anti-clockwise. So there is no need to keep the moment as negative. We have to just keep the magnitude. So once we got the moment, we can say this is moment in z. This is z direction. We can say this is moment about z direction. This is moment about z direction in this way. We can say in this way. So that this is z direction. Or we can say this was your beam. This is z direction, and you are applying load in y direction. So the moment would be developed in this way, so that it would resist the effect of this P into L. So the moment is about the z direction, but it is acting in the plane, that loading plane, y direction. Acting in the direction of that y plane, but the direction of moment is in the z direction. Moment is in the z direction, but it is acting perpendicular to that we call as plane of couple or plane of loading. That's y plane. Okay. Finally, we got the moment, that is 17.32, and similarly for the loading of PZ, that was along the S section in this way. Load was in this way, so we can have that load of P was equals to 10/2, 5 kilonewton. 5 kilonewton for a length of 2 meters. So maximum moment would be m. So load is acting in the z direction. This was your z direction, and so load would be in this way. That moment developed would be in this way, such that this is your y-axis. So moment is rotating in the y direction. So we write moment y equals to 10 kilonewton meter. So we got these values. Now if you want to calculate that second moment of area about x-axis and y-axis. So this is your S section. Earlier you had I section. You had I section. So this was z axis, this was y axis, and dimensions were provided to you. So if you want to calculate the ixx, let's calculate izz first. Izz, the value of izz would be calculated. Let's assume that the overall rectangle would be formed in this way. So overall rectangle of dimensions, the dimensions were provided to you, that this was the dimensions were provided as this was 200. Overall depth was 300, and this was 20, this was 20, and this was 20. And let's say izz you can calculate. This is neutral axis, so you can calculate izz, that equals to the overall rectangle that is formed, that is BD cube by 12, minus, you subtract the part of this one, and this one, the area of this one, the inertia contributed by this one about the z axis. So the area here is, you can say this value equals to 200, or we can say this one, this total is 200. That means the difference, if you subtract this value 20, you get a value of 180. So you can write 180 into depth. What's the value of this depth? So total is 300 minus 20 and minus 20, so 260. So 180 into 260 cube by 12. So finally you got the value of izz, that it would be equals to 186.36 10 to the power 6 mm power 4. And similarly for the value of Iyy, if you want to calculate for the Iyy, let's say that this is your section HH, S section, such that total depth was 300, So this was 300 and this is 200. And this is 20, 20, 20. Now if I want to say about the axis, that's y axis, it would be equals to let's say there are two rectangles. So we write 2 times 20 into 200 cubed by 12, plus we have one rectangle of this dimension 20 for a length of 260. So we write 260 into 20 cubed by 12. So that value of Iyy would be equals to 26.84 into 10 to the power 6 mm power 4. So finally we got the moments also. We got the Iyy and Izz also. So we need Ymax also. Let's calculate the Ymax. From these diagrams, we can say Ymax is also we can solve. So for the Izz, what's the value of Imax? Because the beam is symmetric, we can say Ymax is same. Either you go from top or either you go from bottom. And the corner points are at the same level. So this was your A and B, this was C and D. So they are at the same level and at the same distance away from the neutral axis. So we write Ymax equals to total depth was 300. So we say 150. We can say 150 mm. So we got Ymax equals to 150, and similarly you can get Zmax. So Zmax, we can say this is your Yy, so this is your Zmax. Similarly you have this one Zmax. Zmax equals to that total of 200 by 2, that is 100 mm. So Zmax is 100. So finally you substitute the values. Let's calculate the bending stress because of let's go to the other side. Let's go to this side. Let's calculate that. We write sigma in x direction because of loading in y direction. Or we can write because of py. So that equals to moment in z divided by Izz into Ymax. And similarly, if you write sigma in x direction because of load in z direction, that equals to moment in y direction because of and Iyy into Zmax. This is Zmax. This is not section modulus. This is the Zmax in place of Ymax. And we know the values for mz. We got value of mz. Mz value was equals to 5√3. That 17 point. This one was your mz. 17.32 kilonewton meter. 17.32 kilonewton meter into Ymax of 150. Ymax was 150. So 150 Ymax. 150 by Izz. Value of Izz we have solved. Value of Izz, that was 186.36. 186.36 10 to the power 6 mm power 4, and you got a value of stress equals to sigma x. So you got a value of sigma x equals to, let's keep it as it is. So you got some value, and similarly for the moment y, the value of moment y is equals to moment in y direction. That was moment in y direction 10 kilonewton meter. 10 kilonewton meter. So we write 10 kilonewton meter into Zmax. Zmax was 100 mm. That is 200 by 2. And value of Ymax, Iyy was 26.84, I think. 26.84. 10 to the power 6 mm power 4. So you got a value of say A and you got a value of B. Now, so this is only with magnitude. We don't know why now we are talking about the corners. Let's say this is only the magnitude. This is a value of A and this is value of B. So we got two stresses. Now, if you want to say what's the value of overall bending stress at A, if you want to say what's the value of bending stress at in X about the point A, about the corner point A, about this corner point A, what's the bending stress? So we write that because of loading P, you got a stress value of A, and that's positive. We write tensile stresses as positive and compressive stress is negative. So A plus A plus, and we write minus C. A plus minus C. Because of C that's compressive, we write minus. Because of minus, that value of C was equals to B. We write that value as B. That value as B. Let's write as value of alpha, and this one is as value of beta. Alpha and beta. Alpha and beta. So we can say at stresses in the direction of x at the corner A, that equals to from the conclusions we had earlier, that because of loading y you have tensile stress, so we can write alpha plus you have minus beta. You have minus beta because of loading z you have negative stress of compressor, alpha plus minus beta. So you got a value of minus 23.32 megapascal. That is compressive. Net value of compressive would be there on point A, on corner A. Similarly, if you want to say sigma x at corner B, that is bending stress in the direction x at corner B, that equals to both are tensile. See, from this one we say both are tensile. So both are tensile. That means both are positive. Alpha plus beta. That you get a value of 51.19 megapascal positive tensile stress. Positive. Then after that, sigma x at corner C. So corner C पे आपका 1 is compressive, so alpha is compressive and beta is positive tensile. So you write minus alpha plus beta. So you got a value of let's say you got a value of positive 23.32 megapascal. So it is same value as you got for A, but the direction is that one is compressive and other is tensile. So you got a value of this one, that is tensile. Now finally you write that sigma x at D, at corner D, you got a value of both as compressive. So minus alpha minus beta. Minus alpha minus beta. So you got a value of minus 51.19. That's also same as that of stresses at B. That's one. This was tensile, that means this is compressive. So finally you got the stresses on the different corners of the beam. So this was a very good, beautiful problem of the bending stresses that involved loading in Y and loading in Z. So because of that, you have plane of bending 1 and plane of bending 2. So we had two plane of curvature, we had two plane of couples, and because of that, we had two neutral axes also. So we had two neutral axes. So because finally there would be some resultant neutral axis. So we need to say what's the location of that neutral axis because of this loading, that we can solve in the other problem in the next lecture. We can say this was your principal axis 1, this was principal axis 2. Load is not passing through the principal axis, so that is unsymmetric bending, we can say. And finally we can say, let's say the resultant of the neutral axis passes in this way about the centroid. Let's say this is the neutral axis. Then after that, if you draw perpendicular to that, you had a plane of bending. So plane of bending would be there. So we say that plane of bending does not coincide with plane of couple. So it is unsymmetric bending. So in the next problem we would be solving the location of neutral axis, where the location of the neutral axis would be. So I hope that you understood the problem in a beautiful way. Thank you for watching this lecture from Concrete Path, delivering the facts that matters.